Hi, my name is Denis Timonin and I'm Deep Learning and Machine Learning Solutions Architect at NVIDIA Russia. Today we'll talk about accelerated training with AMP, Automatic Mixed Precision, and TF32, TensorFloat 32 using TensorCores on NVIDIA GPU. There will be two parts in my presentation. In part 1 we'll talk about floating point numbers, about mixed precision motivation, TensorCores. Then we will discuss mixed precision methodology and algorithms. We will look into automatic mixed precision implementation details in different frameworks. We will look into PyTorch usage example. After that, we'll take some complex neural network, some complex GAN, and it will be star GAN version 2. In original implementation, this neural network was trained without automatic mixed precision mode. And we will take the code and we will modify it a little bit to train it in automatic mixed precision mode. And at the end, we will talk about profiling. In the part 2, we will talk about AMP, automatic mixed precision best practices in different frameworks, scientific application and low-level API. We'll talk about the performance of TensorCores, and we'll discuss parameters of data and neural network layers for optimal performance. Why automatic mixed precision and TensorCores are so important things? So all of us know that amount of data is continuously increased exponentially in the last years, and size of neural networks increased too. All we heard about the Megatron LM and GPT-3. So we want to train faster with usage of bigger amount of data and without losing in accuracy. And combination of these two parts, the hardware part is TensorCores and the software part is this is the automatic mixed precision algorithms, helps us with this. Okay, we will start from the beginning, from some simple information, and we will dive deeper into details, into algorithms and implementations. Firstly, we will talk about floating point numbers. Numbers are infinite in real life. They can be infinitely big or infinitely small or infinitely precise. And this is the problem for us because to solve our tasks, we have to present them in our computers, in our memory. And to store them into our memory, we have to approximate them somehow. And after that, store them into our bit cells. There are a couple standard ways to represent real numbers on a computer. It's the double precision FP64 format, single precision FP32, and half precision FP16. What these formats mean and how are floating point numbers presented into memory? Let's take floating point 32 as an example. Number 32 in the name of each format means number of bits that this format will use to store our original number. Floating point 32 will occupy 32 bits, 1 for sine, 8 bits for exponent, and 23 for mantissa. Let's try to simplify this representation. On the slide, we have pi number presented into FP32 bit cells. First part shows us that it's positive number. We see 0 in the first cell. Second part, exponent. This is the window that shows us between which two values our original number is placed on number line. This is some rough approximation of position of our number. In our example, this window shows us that our original number pi is placed between 2 and 4. Window or exponent stores powers of 2 values. So it only shows between which powers of 2 placed our number. Between 2 and 4, between 4 and 8, between 8 and 16, etc. Mantissa clarifies position of our number in this window. In our example, it shows more precise where pi number placed between 2 and 4. And here we can see what is original pi number and how it will be stored in our memory in float format. Our number will be cropped till some length because we don't have enough bits in FP32 to store all other values. It's important to understand that the exponent shows the beginning of the segment where our number is placed. It shows us a window between which integer numbers our real number is placed. The distance between integer numbers increases when the number stored in exponent increase. You can look on the distances between 2, 4, 8, and 16 numbers below. Distance between next numbers on the line is getting bigger. And Mantissa clarifies the position of our real number between these two integers. It divides our section between two integers onto constant number of subparts. Length of subparts increase when the exponent becomes bigger. The closer we are to zero, the more accurately and precisely we can describe the number. And on the right side of the slide we have an example. In Python we can add small number to the small value due to its range more precise in comparison with bigger value. As we discussed, there exists a different format of floating points that use different amount of bits in exponent and mantissa. If our data will be presented with smaller number of bits, that means that we can save memory because we can store more data in the same amount of memory and we can transfer our data faster. But on the other side, smaller number of bits means that we have smaller range and with smaller precision. And two popular formats is FP32 and FP16 are presented on the slide. FP16 or half precision format has 5 bits of exponent and 10 bits mantissa. It result in half the size, but it has a narrowed dynamic range of values that it can actually represent. This is an example of operation where you can prefer to do it in FP32. We have an array of 4096 elements in FP16 and each value filled with number 16. And when we do accumulation, sum operation, our result is overflows. But if you attempt to do that in FP32, it's just fine. Let's look at another example. This is other example of operation that benefits of precision of FP32. And our example is small values plus big values, and the example can be the weights of our neural network. When you upgrading your weights with the gradients that is small, you need a lot of precision to capture that update to continue training. For example, we have weight is 1 and gradient is 0.0001, and in FP16 mode result will be 1 because we don't have enough precision to capture that update. Technical limit of FP16 is 0.0005, and for FP32 it's much better for capturing that small weight updates. A good format strikes a balance. It should use enough bits to deliver precision without using so many, because it slows processing and bloats memory. Two most famous formats in AI and deep learning were discussed previously, but at this year NVIDIA announced another format. It's TensorFloat32 format. The chart on the slide shows how TensorFloat32 is a hybrid that strikes this balance for tensor operations. TensorFloat32 used the same 10-bit mantissa as the half precision FP16 math, shown to have more than sufficient margin for precision requirements of AI workloads. And TensorFloat32 adopts the same 8-bit exponent as floating point 32, so it can support the same numeric range. The combination makes TensorFloat32 a great alternative to FP32 for crunching through single precision math, specifically the massive multiply accumulate functions at the heart of deep learning and many HPC applications. Also, here's presented bfloat16 format. The dynamic range of bfloat16 is similar to single precision format. Relative to FP32, bfloat16 sacrifice precision to retain range. Okay, let's talk about the mixed precision now. As we saw, we have multiple precision formats, and core idea in mixed precision training is we want to use reduced precision numbers to make things faster and to build bigger models, to use bigger mini batches and so on. And we will use reduced precision FP16 as much as possible for speed and scale. But at the same time, we will identify the parts of the model that needs full precision, and we'll use FP32 in these parts. So goal is to combine benefits of multiple precisions. And combining these two approaches, we will get multi or mixed precision mode, multi or mixed precision training, and we can maintain complete task specific accuracy with higher training speed. And this approach can be applied to any models, to image classification, natural language processing, or generative models. Now understand what is core idea behind mixed precision training, and but at the same time we need to have hardware that can process our operations in different precisions and that can process it fast. TensorCores, this is special hardware that was designed specifically for deep learning and training into automatic mixed precision mode. Specialized hardware execution unit for performing matrix multiplication and convolution operations. The first generation Tensor cores in NVIDIA Volta deliver cool performance with mixed precision matrix multiply in FP16 and FP32 over NVIDIA Pascal. Tensor cores do operations with vectors of scalars. They multiply as vectors per 1 GPU clock. On the video you can see the Volta or Turing Tensor cores performance in comparison with the Pascal architecture. These tensor cores are inherently mixed precision. They take as input FP16 values and doing multiplications of rows and columns. And the result of multiplications will be stored in FP32. Accumulation happened in full precision, and this full precision part helps us to maintain the accuracy. And as the user, you don't have to think about the hardware level because all of the operations are implemented into cuDNN and cuBLAS libraries on the low levels. On this slide, we see comparison of TensorCores version 2 with TensorCores version 1. TensorCores version 2 was presented in Ampere architecture. TensorCores version 1 had support of FP16, int8, and int4 in different architectures on NVIDIA GPU. TensorCores version 2 has an additional support of FP64, TensorFloat32, and bfloat16 types that were discussed previously. TensorCores version 2 takes as input FP32 vectors, convert them into TensorFloat32 values, and do multiplications of rows and columns, and the result of multiplications will be stored in FP32. So they act as a regular tensor cores. They operate the vectors but with more bits in it. That means that we can use native FP32 training pipeline, and on Ampere architecture it will be processed on tensor cores without automatic mixed precision. But of course, if we will use automatic mixed precision with FP16, we'll get even more speed. And main NVIDIA Ampere architecture enhancement, there are the new tensor cores design that has 2.5 bigger throughput for dense operations in comparison with V100, sparsity support, and the bfloat16 format that has the same rate as FP16. We discussed floating point formats, discussed motivation behind mixed precision, and we discussed hardware. And as a result, we will combine hardware tensor cores and automatic mixed precision methodology to train neural networks. Our goal is to keep stored values in half precision, weights, and activation along with their gradients, and use tensor cores to accelerate math and maintain accuracy. And the benefits are up to 8x math speedup and half memory traffic and half the memory storage. Years of networks trained with 60-bit formats. proving to match FP32 results across a wide range of tasks, problems, domains, deep neural network architectures. And the chart only represents a small sampling of neural networks trained in mixed precision. And the main information is if you have a model and if you want to train it, so this is for you. Use automatic mixed precision approach or TensorFlow 32 and train on TensorCores on NVIDIA GPU. We shortly discussed the mixed precision training and TF32 training. TF32 format on Ampere architecture doesn't require any additional algorithms and changes in your code to use it. So we will look at example of its usage later. And now let's talk about the technical details of automatic mixed precision AMP and about the algorithms and methodology behind AMP training that helps us use FP16 in our neural network and to train without losing the accuracy. Okay, the mixed precision methodology for training. So goal is to training with FP16 in general purpose, not only for a limited class of applications. For all class of applications, FP16 has not so many bits, and the things we need to think about when we training in mixed precision is there are two big parts. First one, the model conversion, and we have to worry about non-TensorCores operations, non-native TensorCores operations. And second, steps 2 and 3, we will combine these steps together. These steps are about how to handle computation of gradients and using of gradients to take each optimized step. First step is model conversion. If you want to use TensorCores into deep learning frameworks, you have to do two steps. First step is to use FP16 values for the weights, layer parameters of your neural network, and second, ensure that the inputs are FP16 too. So the layer runs on TensorCores now. So after that, your operation will run on TensorCores, of course, if you have hardware with TensorCores. And here are some examples of in different frameworks how to turn on TensorCores. API may be a little bit outdated, so just check into documentation. Let's talk about things that are running on TensorCores. TensorCores are about matrix multiplications and convolutions. It's important to understand that. Matrix multiplications and convolutions can be used on TensorCores hardware without any scares. So if you have model with only matrix multiplications operations in it, that's perfect case and you will achieve good performance. But in reality, it's not true. Models has a lot of layers with lots of details, and we have grouped some operations into four main groups. Activation functions, normalization functions, loss functions, and others. And the main question here is, can we convert all of these layers directly into FP16 or not? And what operations are good for TensorCores and in what form? To understand that, we will return back to the basic structure of TensorCores. What are TensorCores doing? They take in inputs in half precision, and output of multiplication is kept into high precision. And sum of all of those products will be accumulated into FP32, into high precision too. And main idea is that matrix multiplication and convolution operations are secured on the hardware level. It's really important. So we will not lose any important information for these ops when we'll do any operations on TensorCores. But this doesn't guarantee the same for other neural network operation types. And those two principles like keep intermediate or temporary values in high precision and perform sums or reductions in high precision too. This principles to keep in mind when we talk about non-TensorCores operations. We discussed two main principles, and one of them was to keep intermediate or temporal values in high precision format. Let's talk about this a little bit. Most of the time this doesn't come up. Many pointwise ops that you're gonna do are generated to operate directly on FP16 values. The one place that it really isn't true is for function that has swing in dynamic range, when the small values become very large and large values become very small. That's because dynamic range is limited when we use reduced precision format. And now we're talking about functions like exp, log, or pow. And as example, we have soft plus, some activation function, and if we look at its graph, there is nothing scared. It's like ReLU, and it seems like that all of its computations can be done in FP16 mode. But if you will look into code, it's actually pretty easy for things to go wrong in mixed precision, because we have intermediate value, and whole function soft plus of 1000 will be 1000, and it's okay for FP16, but intermediate representation exp of 1000 will overflow, and that's the problem. And the solution is to cast inputs in FP32, do computations, and cast outputs back to FP16. That was theory that will help you to operate with your custom code, your custom layers, custom loss functions, and so on. But in reality, mostly you don't have to do anything for non-linearities, and they can be run in FP16, except the exp, log, and pow functions, as we discussed previously, especially when they embedded inside. Some additional points: for normalization, you need to cast into FP32, and for last functions, it's almost always a good idea to run your function in FP32. We are finished with the first thing, and the second thing is master weights. What is this? And let's talk about look into the picture. So we are doing some training. For example, we have some weight values. We've computed the gradient for the values. We've computed some partial derivative for the particular value. We have some optimizer and so on. And so we computed update for that weight. And if my weight in small precision format, then step size between two representable values in that format is bigger than in full precision formats. For example, for FP16 with 10 bits of mantissa between values 1 and 2, the step size is 1 over 1024. And if my current value is 1.5, current value of weight, and the next biggest representable value is 1.5 plus 1 over 1024. And if your weight update is, for example, 1 over 4000, this update value is too small, and the result of our updating step will be round back to 1.5. And in practice, it's really to understand, but in practice, your training model and loss getting smaller over time, and there is some threshold. After that, your loss stops changing. And master race, this is the main recommendation to handle this. It's about the having copy of weights in full precision mode. So this leads to a situation when we have two copies of our model in the memory of GPU, and one of them in FP16 format and other in FP32. One for computation, second copy for weights updates. But this saves us from additional problems, and this approach is default behavior for main implementations of AMP in main frameworks. Some note here, so not all models have this problem, but it's a general purpose. Okay, we are finished with the first point. The second point is the master weights. Let's talk about the picture. We are doing some training. We have some weights value. We've computed the gradients for that value, some partial derivative for particular value. We have some optimizer and so on. So we've computed update for that weight. And if my weight is small in small precision format, then and what is the problem here? And the problem is we can't detect underflow. We can't distinguish between just real zero values and the gradients rounded to zero. But we can apply a trick named loss scaling. If we scale the loss up by k, some constant, mm, by by the chain rule of derivatives, gradients will also be k times bigger. We are shifting gradients to the dynamic range that is good for FP16 precision. And we can scale up our loss and we will save our gradients from underflow. It's okay, but the new problem is gradient overflow. This happens when the values goes beyond the range of values that can be covered by FP16. And overflowed values will be replaced by infinity in that case. But unlike gradients underflow, gradient overflow is easy to detect. We can scan our values to find inf in it, and when inf is detected, we can scale the loss down. So for us, it's better to have bigger than smaller scale factor. And at the beginning of the training, we're setting up scale factor value to some big number. And the final algorithm for loss scaling is we start to train with some big scale parameter for loss. Every time the gradient overflows, so for example, we're detecting infinite numbers in our matrices, we reduce the scaling parameter by a factor of 2. And if the gradient haven't overflowed in the last n updates, it's about 1000 usually, or 2000 like in PyTorch, then we increase the scaling parameter by a factor of 2. And the figure shows how the scale factor changed during training. Let's combine all of these rules together. So this is how automatic mixed precision training cycle looks. And at the beginning, we are getting FP16 weights and master copy of weights in FP32. The two copies of weights of the same weights stores on the GPU memory. And after that, we do forward pass, compute our loss in FP32. As we discussed, loss function is better to compute in FP32. After that, we're going to scale that loss, do a backward path computation of gradients, and if we detect an overflow, we just skip this batch and just scale down our loss. And we start from the beginning. But if grades is good, we're doing copy of FP16 gradients into FP32, unscale them, remove scale, and update our FP32 version of master weights. After that, we can convert master weights into FP16 version and continue to train. And this is the complete picture. Let's move from the algorithms to the code. Let's talk about how you can use AMP to train your models and how to turn this mode on into different frameworks. First, we will talk about TensorFlow 32 support, how to train model in full precision on Ampere architecture. TensorFlow 32 mode is default mode for A100 GPU in new releases of NVIDIA NGC containers. It's supported by multiple frameworks, and operations that are supported is single precision convolution and matrix multiply layers, including linear or fully connected layers, recurrent cells, and attention blocks. TensorFlow 32 acceleration is not enabled for convolutions or matrix multiply layers that operate on non-FP32 tensors. It's not enabled for any layers that are not convolutions or matrix multipliers, and it's not enabled for optimizers and solver operations. So, but for all other operations that are supported by these TensorCores, computations will be done on TensorCores on A100 NVIDIA GPU. So you don't have to worry about TensorFlow 32 TensorCores training. It's turned on by default and you don't have to change your code. There exists an global variable NVIDIA TF32 override to toggle TF32 mode at system level and override libraries and frameworks. Now we're returning back to AMP training. All these rules that we discussed before are already implemented in high-level frameworks for deep learning, and implementation looks quite simple and it's easy to use it. Usually you have to add a couple of additional code lines into your original code to turn on AMP. In many frameworks, implementation of AMP support looks similar. Here we have example of AMP support in PyTorch. In older version of PyTorch, AMP support was implemented in separate library created by NVIDIA. It's Apex library. But from version 1.6, support of AMP is natively included into PyTorch and you don't have to use Apex anymore. Let's have a look at the code. There are two main parts. One part is the autocast. This is the casting part. We are casting our model to FP16 mode and storing FP16 weights and FP32 weights on GPU. And second, we have scaler. We have scaler that scales our loss to prevent underflow and overflow, as we discussed. And that's it. You don't have to worry about training, except some custom losses or norm or some hardcore non-linearities if you are using them in if P16, for example, as we discussed on previous slide. And of course you have to run your code on GPU with TensorCores. You can run AMP training on GPU without TensorCores too, but this will slow you down because FP16 training will be emulated on software level. And there are examples for TensorFlow, MXNet, and PaddlePaddle frameworks. Here's an example of full AMP training pipeline in modern PyTorch. Firstly, we'll create model and optimizer in the full precision. Usually it's FP32 creates a grayscaler once at the beginning of the training, runs. After that, we starting to train and runs the forward pass with autocasting. We getting the loss that were computed with the FP16 weights of our model. After that, we scales the loss, calls the backward on scaled loss to create scaled gradients. After that, we are doing scalar step that firstly unscales the gradients of the optimizer, and after that we update the scaler for the next iteration. Some deep details about how autocast and gradscaler works. Autocast, this is the Python context manager, and it has a couple of lists that contains the names of the PyTorch ops and PyTorch neural network layers in it. It's whitelist that contains the functions where we expect a speed up with FP16 math, like convolutions and matrix multiply, and the blacklist that contains the functions for which 16 bits of precision may not be sufficient. So we want to ensure that inputs are in FP32. And so when we are doing forward path in autocast context, PyTorch goes through our layers and ops in our model and scans our white and black lists to understand in which list our current op is placed. If our operation was found in whitelist, that means that input can be casted and we can run this operation in FP16 mode safely. Otherwise, it will be FP32 computations. GradScaler is a simple class that has a couple of methods to scale, unscale gradients, and apply gradients if inf values was not found. And it's important that GradScaler can track multiple losses and multiple optimizers if it's needed in complex cases like GANs. Now we know how to use AMP in different frameworks, and we saw how to start to train a simple model in AMP mode. So if you don't do that still, call to action is go and train in AMP mode. But what about more complex neural network models with multiple neural networks and in it, like GANs, and multiple losses maybe, and optimizers? Let's talk about this now. To demonstrate AMP training for some complex cases, I took neural network that is quite complex and its implementation didn't have any publicly available code for AMP training. This is StarGAN version 2 that was presented on CVPR 2020. This is some combination of neural networks for image-to-image translation to apply style of one image onto another. And we want to modify our code to train faster, and that's it. And we know that it's quite simple to add AMP into our training pipeline without diving into details. So let's try to do this. There are 4 different neural networks that train together in StarGAN version 2 to transfer images. The generator translates an input image into an output image, reflecting the domain-specific style code. The mapping neural network transforms a latent code into style codes for multiple domains, one of which is randomly selected during training. The styler encoder extracts the style code of an image, allowing the generator to perform reference-guided image synthesis. And the discriminator distinguishes between real and fake images from multiple domains. This is the main description of construction of neural networks. We don't have to dive into details deeper because all we want is to modify our code to train faster. Let's look into our original training cycle. Code written with the usage of PyTorch framework. We know that all we have to do is 2 things: cast our model with autocasting and scale our loss, and use our instance of scalar class to update our parameters. What's changed from previous example? Here we have 4 models and we are doing 6 optimization steps per 1 iteration. But this doesn't change our plans a lot. We use autocast context when computing forward and loss value of our models. Each forward call wrapped into separate autocast context because between forward calls we have to do backward passes, and backward passes over autocast are not recommended. We have only one instance of scalar, one instance that supports all of our losses and optimizers, and this one scalar scales all of our losses and it saves all scaling constants for all losses internally. In comparison with Apex, if someone used it before, we had loss ID parameter in scale function. Here we don't have it. And then we are doing scalar step operation after call the backward function. One thing that is not good here are the calls of scalar update function. Usually update function must be called once per iteration cycle, and this is the official recommendation from the creators of the AMP plugin. The reason for this is that it updates scale constant parameters for all losses simultaneously. But at the same time, the scalar denies the ability to call backward multiple times without updating parameters between these calls. So that StarGAN v2 is some complex and unregular example where we have to do multiple call of update function between multiple backward steps with the same optimizer. And here is the example. We have to do two backward steps with the same optimizer per one training iteration. And to do that, we have to call update function. And it's fine to do that, absolutely. The training works, and the problem absolutely is not so big, because by calling the update multiple times, we will just update our scaling constant multiple times faster. One more thing, when I started to train, some error has occurred. The text of the error was lerp CUDA is not implemented for half. Here it is, and lerp CUDA is an interpolation operation, and it was not implemented for FP16 mode. And what's more important, it was not included into white or black lists of operations. That's why we've made this bug. And this bug will be fixed, but when you will face some similar bugs, all you have to do is to change your code manually, just by casting your parameters into format that function supports, and casting outputs of the function back to the original format. Below is an example of code that fixes the problem. As a result, training time till convergence decreased from 3 days to 1.7 days on V100 GPU. And I achieved near the same accuracy in my training procedure. Near the same accuracy because diff in matrices that I achieved was less than a couple of percents. But neural network generates images successfully and everything works fine. And a little bit difference in metrics most likely was due to I've made only one attempt of training, and I've changed hyperparameters of this training pipeline. I've changed batch size a lot, and I've changed number of iterations due to change it by batch size. So I've changed hyperparameters, and this diff in metrics have to be fixed by fine-tuning hyperparameters again for AMP training. So we can fine-tune the model with lower batch size at the end to achieve the same accuracy, or we can fine-tune hyperparameters again for new batch size. We can increase the number of iterations of training. Okay, so call to action. TensorCores will be everywhere soon, and what you have to do is use GPU with TensorCores. For example, RTX 20 or 30 series, or for example A100 or V100 or other GPU with TensorCores. Use AMP and train all of your neural network with TensorCores faster with native AMP support in frameworks. If some errors arise, now you know why it may happen. So fix them manually and create an issue on GitHub in the frameworks repo. And the last thing, how to make sure that you are using TensorCores in your training pipeline. The simplest way is to use NVIDIA Deep Learning Profiler TensorBoard plugin in the latest NVIDIA NGC containers. You can run your code with dlprof. The event files will be created, and after that you can run TensorBoard and use event file as a logdir. What you can see in TensorBoard, you can see the nodes that are using TensorCores and nodes that eligible for TensorCores. Other way to check TensorCore usage and their efficiency is profiling. There are a couple of ways to run profiling into NGC container. For example, you can run in sysprofile, and then you have to open output file with output file name in NVIDIA Inside Compute application. That can be downloaded at NVIDIA site. And this and other similar substrings in the name of the kernels shows us that this is TensorCore kernel. And my colleague Dmitry Mironov is also presenting on DataFest. He dives deeper into profiling of deep neural networks. So if you are interested in this, do go and check his video out in SysML track. And here is the link. In the part 2, we'll talk about deep practical advices applicable to AMP training, about corner cases, scientific usage and hardcore optimization that will help you to train faster and to avoid some errors in AMP mode. Firstly, some simple cases and advices. If you're using PyTorch as a main framework, so use PyTorch 1.6 or later version and native AMP instead of Apex library. Developers from NVIDIA and PyTorch community has analyzed architectural errors that was made in Apex and fixed them in PyTorch version of AMP. Other PyTorch AMP advantages is it's faster due to less Python overhead. What's overhead? As we remember, we have to cast our model layers and inputs into FP16. And in the case of Apex, it was Python wrappers on the Python side. For the PyTorch MP, cast wrappers are on the C++ side and tightly integrated with PyTorch Eager mode dispatcher. Other advantages is guaranteed PyTorch version compatibility because it's part of PyTorch, no need to build extensions, Windows support, bitwise accurate saving and restoring of checkpoints. In Apex, you had to write some additional code to restore checkpoints, and some other advantages. PyTorch version of AMP has more native and intuitive API in comparison with Apex. This is my point of view. In Apex, you have levels of AMP 0, 01, 02, or 03. And main levels are in 01 or in 00 mode. Mixed precision is turned off, and this is just regular FP32 training. In 01 mode, AMP is turned on with master weights and low scaling, and this is standard mixed precision training with TensorCores, as we discussed before. And 03 mode, this is when you don't have master rates in the memory and you only have one copy of the FP60 version of the model in the memory of GPU. It's hardcore case, you can achieve a little bit more speed, but training procedure can be interrupted by one of the errors that we discussed before. For example, some nonlinearity or activation functions will overflow. In native AMP, you have more nicely looking API, and you have autocast context, and using it you will start to train in AMP mode like 01 mode in Apex. And you have half method, so you can cast your model straight into FP16 and you can start to train in fully half precision mode. It's like 03 mode in Apex, but you can met overflow or stop to wait updates. Theoretically, you can manually cast model your neural network into half precision mode and train without autocast and scalar instance. It's similar to 03 level of AMP mode in Apex. But there are a couple of things that you have to worry about. So you have to warm up your model for a couple of iterations in FP32 to in FP32 mode to avoid big losses and gradients, to avoid overflow. You have to check that your training didn't stuck on some iteration due to small gradients. You have to check all components and variables that they were successfully converted to FP16. For example, default epsilon will be rounded to 0. And half precision mode training will give you roughly about a couple of percents of training speed and possibly a little bit bigger batch size. Some other advices, please do not forget to add autocast into validation, evaluation, or testing parts of your scripts to avoid errors. Other advice, if you want to work with the gradients in your training pipeline, in your training cycle, maybe you want to analyze them, clip them, or accumulate, you have to unscale them first. So this is the link with the instruction of how to do that. Other advice is parameters of loss scaling can be configured, scaling constant can be configured, and other advice, you can turn off autocasting in some parts of the code. Other advices, if you're training multiple neural networks in the cycle, you have to reinitialize grayscaler instance for each iteration. This is important for example, for such tasks like neural architecture search, when you're training a lot of neural networks and in the cycle, yeah, step by step. And other advice, if use fused optimizers like fused Adam, fused RGD, and so on, use them in AMP mode and in regular training mode, in FP32 mode of training. So because they do fused and multi-tensor apply launch of optimizer. This will improve your speed. And fused optimizers are already implemented in Apex library, and soon they will be added into PyTorch. Pull request already created. And the last advice, prefer binary cross entropy with logits function over binary cross entropy when you're using AMP. This is just internal advice from the creators of the PyTorch AMP. Now let's talk about normalizations, about different normalization layers that exists in deep learning frameworks. So layer norm normalization, this layer usually uses FP32, but in practice is okay. It's okay to cast it into FP16. So this is some advice from developers from Facebook, and also you can use fused layer norm implementation from Apex. And uh, for batch norm, uh, you can use FP32 and FP16 inputs and outputs, but parameters have to be in FP32. And in this mode, batch norm will use cuDNN implementation of the layer, and it can be faster. For distributed training, you can use synchronized batch norm layer from Apex 2. Okay, and spectral norm. Regularization technique spectral normalization is quite popular layer, especially in GANs. And PyTorch implementation of this layer does not fully optimized. So my colleague Mingyu Liu proposed some code that do computation of spectral norm and normalization of eigenvalues with the support of half precision mode. And you can find this code on the slide or by using this link that I provide. And the link on the slide is very interesting. It's a list of tutorials about the AMP prepared by NVIDIA Lab. And there are a bunch of tutorials, useful videos about TensorCores, about training different neural networks like LSTM, GANs, 3D convolution models with the support of the TensorCores. And also some separate video which is called PyTorch Performance Tuning Guide that will help you to get more speed from your training pipeline. Now let's discuss TensorCores scientific application and low-level API. You can use C++ API to program TensorCores behavior. You can get fast matrix multiplications in your C++ programs with reduced memory traffic. On the right side of the slide, you can see simple examples of C++ usage, and there are examples for FP16 and bfloat16 formats. We discussed bfloat16 format previously. You have to include header files to use them, of course, and PyTorch and Python frameworks don't have support of the bfloat16 format. It's in plans to include it in PyTorch, but for now you can use it by using C++ CUDA API only. And so if you're interested in bfloat16 use cases, so use C++. Behavior of TensorFloat32 in libraries for A100 for developers using NVIDIA libraries. Default behavior of TF32 mode for N100 is in cuDNN and deep learning frameworks. TF32, TensorFloat32 is default mode, and FP32 computations implemented in these frameworks like convolutions will be on TensorCores by default, and you can use environment variable to turn it off. And in cuBLAS, a library for linear algebra operations for scientific research, you have floating point 32 mode by default due to more precision required in HPC applications. And you can turn on TensorFloat 32 mode with environment variable. TensorCores can be used for scientific computing in scientific applications as well. And here we have a link and successful case when researchers used combination of FP16, FP32 and FP64 to achieve great performance increase in the task of earthquake simulation. They used mixed precision approach to achieve great speed increase with the same accuracy. And on the right side we have additional link with the guide and example of how to program TensorCores in CUDA 9. In my presentation I want you to understand all aspects of TensorCores, to use them in your projects and understand in details what is happening on all layers. And now let's return back to deep learning. And this is the final part of whole presentation. The main question that we'll try to answer is how to design your training pipeline, data pipeline and architecture of neural network to maximize workload of TensorCores. How to choose the size of data batches and size of parameters layers of neural network to achieve optimal performance. Batch size, number of inputs, outputs in fully connected layers, number of filters in convolution, and so on. And usually it's bad politics to use maximal batch size to fill in your GPU memory. It's easiest way but not good for us. And what is good? There is no universal answer, but we'll analyze main components of GPU working pipeline to form rules that will help you to maximize GPU workload. Here are three main components that we need to understand to maximize GPU load up. And first, math limited and memory limited operations. Second, parallelization and tile quantization. And third, parallelization and wave quantization. As we talked previously, TensorCores are good for matrix multiplications and convolutions. But if to say more generalized, TensorCores are good for math-heavy operations. Math-heavy operations benefit from TensorCores at the same time, and convolutions and matrix multiplication operations have to be math-heavy too to benefit from TensorCores. And what math-heavy means? On the right side we see a GPU, highly parallel computer, and it has memory and cores or processors or SMs that have these cores in it. And two main big parts that rely on performance is bandwidth of memory and throughput of cores. Again, SMs on the picture. SM is streaming multiprocessor, and this is minimal cell that will run your task. So A100 has 108 SMs. And when computation operation starts, some of your data will be divided into blocks, and SMs will fire up to compute these partial subtasks. And what GPU and any computer do, it reads the data from memory, do some computations, and return back the results into the memory. And which of these two main operations takes longer? Because longer operation is bottleneck. So if computations on TensorCores requires more time than uh, read or write operations, that means that pipeline is math bound, math heavy or math limited. Otherwise, it's memory bound. So for A100, the throughput and bandwidth numbers are presented on the slide. We have 312 teraflops is compute power for TensorCores in FP16 mode, and 1.5 terabytes per second is bandwidth for DRAM. And for TensorCores, it's good to operation to be math bound, math limited. Let's turn it into practical things for us. So math limited operations is if the time we expect to spend on doing math is bigger than time we expect to spend on fetching from memory. So how to compute this? We are taking numbers of operations that our neural network or layer is doing, a number of multiplying and adds, divided by math throughput of GPU. We already have these numbers from white paper about our GPU. And comparing that with bytes that we will read and write for that computation, divided by memory bandwidth. Equivalently, we can rearrange the same equality to have ops to bytes to byte ratio, and we will get GPU constants on the right side and parameters of our layer on the left. And we can compute how good our layer for TensorCores and how varying of different params like batch size may affect on performance. And let's do these computations for fully connected layer in FP16 mode. Fully connected layer with 4096 inputs and outputs. And in batch, this will be the variable for batch size. So arithmetic intensity will be the number of outputs multiplied by batch size and multiplied by number of inputs multiplied by 2. And in denominator we have number of memory operations needed, and this will be the number of inputs multiplied by number by batch size, and batch this is the number of reads that we have to do to read the data input data from our GPU memory, plus number of inputs multiplied by number of outputs. This is the number of reads operations that we have to do to read weights of our fully connected layer, and number of outputs multiplied by number of and batch size. This is the number of write operations that we have to do to write results into GPU memory, results of our layer. So as a result, we have this formula, and this is like 4096 multiplied by batch size divided by 4096 plus 2 multiplied by batch size. And this is the arithmetic intensity of our fully connected layer with these parameters in flops per byte. And for the right side of our equation, we have constants because we do computations on A100 GPU in FP16 mode. We are taking these numbers from previous slide. We're dividing math bandwidths by memory bandwidths, 212 teraflops divided by 1.5 terabytes per second, and this will be 201 flops per byte. As I said previously, 201 flops per byte, this is the threshold. If we are getting bigger number of operations for each byte than 201 operations, that means that we have math heavy operation. And if our number of operations per byte is less than 201 flops, so we have memory heavy or memory limited operation. Okay, and on the right side of our equation we have 201 flops per byte. We compute this value from constants for our A100 GPU in FP16 mode on TensorCores. So this is the threshold to divide memory limited and math limited operations. And on the left side we have parameters and equation for our layer. And we can vary batch size to move our math intensity. And here is the results on our graphic on the right side of the slide. Horizontal green line on the graph is threshold for math intense ops. In blue is math intensity of our layer, which depends on batch size. As the batch size increases, we go from being memory limited to math limited. And from some batch size, value of our fully connected layer is good for TensorCores to overload our TensorCores. We are coming to the second part now. We've discussed batch size and how it affects on matrix multiplication operation, discussed math limited and memory limited fully connected layer, but how matrix multiplication and fully connected layers works on GPU in general. So GPU is a highly parallel device with a lot of cores. So GPU execute work by mapping their computation into threads, some tiny lightweight threads, not like CPU threads. And these threads are grouped into thread blocks. And GPU takes these thread blocks and gives them to one of the SMs. We saw previously that A100 has 108 SM. This is like minimal compute parts of GPU. And so we can divide our matrix multiplication computation on subparts, on some smaller subparts, to load them into all SMs and to compute matrix multiplication in parallel to get efficient parallelization of our procedure. And so for matrix multiplication, we are splitting the output matrix, C matrix here on our slide, into tiles of some size. For example, we have green tile with the size m by n. And for each tile, we are going through corresponding regions in input matrices A and B that contributes to that tile. And using this tile, we can parallelize our computations on our SMs. Again, we will divide matrix into small tiles and we'll load them to the SMs to compute in parallel. Let's look at some simplified example. We have to calculate 40 by 40 matrix as a result of our matrix multiplication operation. And we have GPU with 16 SMs as an example now. And we know that for each SM is better to operate 10 by 10 matrices. And this means that our tile size will be 10 by 10. So we can split our matrix perfectly evenly. 4 tiles exactly on each side. And we have 16 tiles in total, and that can be loaded to 16 SMs, 1 tile per SM, and can be optimally computed on our GPU. Now let's consider we have 40 by 31 matrix, and all other parameters is the same as previous. We have same GPU and same tile size. But what we get is one side of our matrix is not evenly divisible, and in our matrix we have only 3 columns that are filled and one tile that is almost entirely empty. And we are wasting work on this empty portion of the tiles, and this is the case that we call tile quantization. And here is what it looks like on actual measurements on V100 GPU. And there we have 3 graphics with throughput on the left side, latency in the middle, and a number of tiles on the right side. This is matrix multiplication task for matrix with sizes 20,480 is our number of output channels and 4096 is our input channels. And n is our batch size that we can vary to move to get different performance. And graphics shows us how much size affects on these 3 parameters. For batch size 128, we're getting 100% utilization and perfect case, perfect speed and perfect performance. If we make it one wider, we're adding additional columns that are mostly unused, and our utilization splits in half and performance dramatically decreases. If we will continue to increase batch size, our tiles will be less and less unused till 256 case when we will achieve perfect utilization again, and so on and so on. And if we will look onto duration graphic, this means that if we have 129 batch size, this is the same as get 256 batch size. It's literally the same cost. So advice is choose your main dimensions to be multiples of 64. It will be better to choose multiples of 128 or 256, but 64 is enough case. Other option, we have 40 by 50 matrix. All other parameters are the same. We are dividing on 10 by 10 tiles and evenly divisible, but we have 20 tiles which is divided between 16 SMs now. And so in first iteration or first wave, our GPU will use 16 tiles to compute the simultaneously. But in the second iteration, in the second wave, we have 4 tiles and 60 SMs, so 12 SMs in the next iteration will be idle. That is also wasted work, because we have to wait 2 waves to compute, but at the second wave our SMs just do nothing, and that is the wave quantization problem. And so our number of tiles, our number of blocks, has to be multiple of number of SMs on GPU, ideally, to avoid this. And in practice, charts look similar to the charts from the tile quantization problem. Again, we have m, k, and n parameters, where n is our batch size, and the effect is similar to previous slide again. So we have output size 1280, input size 4096, and so for batch size 2048 for V100 and these parameters of the fully connected layer, everything is perfect and we have a 100% utilization. But if we have batch size that is not perfect for tiling, 2049 for example, our performance drops twice, and it's almost equal for us to use 2049 and 4096 batch sizes. We will get near the same accuracy and near the same latency, sorry. And but in real use cases, ResNet, for example, neural network, we have thousands of tiles, and effect of performance drop is not so dramatical for us. But if you have small layers in your neural network with small m, n, and k, so effect effect can be huge. We have observed three main problems and what is advised for us. What are some best practices to use in your training and inference pipelines? It's hard to take into account all of the nuances, but so practical advices and some cheat sheet are provided on the slide. So first, make sure TensorCores can run efficiently by aligning k dimensions to 128 bits. This means that for FP32 mode, k dimensions have to be multiples of 4, for FP16 mode multiples of 8, and for int8 mode multiples of 16. K dimensions is for fully connected layers are input, output, and batch size. For convolutional layer, input and output channels count, and for recurrent layer, mini batch, hidden state size, embedding size, and vocabulary sizes. Second, provide enough work to fill the GPU. Choose k dimensions larger than 256 and at least one substantially larger to be math limited. Our main target is to be math limited. Third, aim for good tile and wave efficiency, especially when at least one dimension is small. Choose k dimensions to be multiples of 64, 128, or 256, and ensure the number of tiles is multiple of the SM count. You can find SM count in a white paper or instruction for GPU, and as we remember, A100 has 108 SMs. And it's really important, if you can't follow every guideline, following as many as possible still helps performance. And for more information, just visit this site. And here is real-life example. We will talk about transformer model. Neural network from the paper attention is all you need. By default, it was created as neural machine translation model to translate from one language to another language. And without going into details, transformer has a lot of fully connected layers, matrix multiplication layers in it. Let's look at first fully connected layer with 1024 inputs and 4096 outputs and some number of tokens per batch. Some of default tile sizes on A100 is 128 by 128. So we divide 4096 by 128 and our number of tokens per batch by 128 too. Multiplying these two numbers, we are getting number of tiles. So what number of tokens per batch should we choose? If we will use power of 2 values, we'll produce 1024 tiles, and this is 9 full waves plus a 52 tile tail, and this is not optimal case and not get perfect performance. But getting smaller batch size, 3456 tokens, we will produce 8 full waves, and we will not get any idle tiles. 3456 is divisible by 108, this is the number of SMs, and by 128 bit lengths. So with smaller batch size, you will get more efficient training overall. It's roughly about 7% more efficient. And thanks for watching.